Hello, hello, sir. This is Ombadu Chetri from Group DC7, and I hope you are doing very well in this lockdown and you are staying safe. So, before starting my presentation, I would like to say something about my agendas. My topic is dinic algorithm or dinic algorithm. So, before starting with the presentation, let me take you through the agendas. First of all, we will be discussing about the introduction to the dinic algorithm. Then the introduction will be followed by story of this algorithm, pseudocode, and we'll be discussing more about complexity analysis, what are the applications and real life application of dinic algorithm. Then I'll be showing about the problem, definition. then the then we'll be discussing about limitation and conclusion of dinic algorithm. So let's start with the introduction. Dinic algorithm is also known as Dinic algorithm. Dinic algorithm, it is a strongly polynomial algorithm for computing the maximum flow in the network. It is strongly polynomial algorithm because its runtime does not depend on the capacity values of the flow graph. So the basic principle of dinic algorithm is maximum flow is equal to minimum cut. So I'll be telling you about maximum flow in next slide. So dinic algorithm is one of the fastest and revolutionary algorithm that pushed the area of network flow ahead. It is very similar to the Edmonds-Karp algorithm and the very new concept of level graph and blocking flow were introduced in this algorithm. So what is maximum flow? The maximum amount of energy or flow that the network would allow to flow from source to sink is called maximum flow. The maximum flow can be calculated by looking at the flow value of edges leading to the sink. I'll be showing about what is maximum value in the graph. So here the S in the graph represents source and T represents sink. The maximum amount of energy that is transferred, the maximum amount of energy or flow that is transformed from the point S to T, it's called maximum flow. So let's get back to introduction. So the algorithm runs with the runtime of big O of b square E. So let me take you through the history of this algorithm. It was invented by Israeli computer scientist called Emif Deniz in January 1969. It was developed by Israeli computer scientist in former Russia called USSR. It was published in a journal called Doklady Academy Nok SSR in 1970. It was further developed by his students, by two students. The name of his students were Itai and Ivan, and they combined BFS breadth first search and DFS search to further develop it. So the application of dinic algorithm is are listed as maximizing the transportation with given traffic limit. It is used to maximize the packet flow in the computer networks. It is also used to find the maximum flow in the network. Now let me take you through some real life examples. It is used in airline scheduling. It is also used in baseball elimination and image segmentation. So the complexity analysis. Here we can see the best case time complexity, worst case time complexity, and average case time complexity is same for three of all. It's big O of E V into E V square. So the space complexity of this dinic algorithm is big O of E plus B. Now pseudocode said equal to 0 for each E in G, construct a GL. Here GL represents the graph level from GF of G. If this T is equal to INF, then stop and output, then we have to stop and print our result. And then again we have to find a blocking flow FP in graph level, and then augment flow. Then we have to find augment flow by FP, and after finding augment flow, we have to repeat from step 2 until the algorithm stops. So here are some terminologies about dinic algorithm. Basically, what is level graph is the one where each of node is shortest from the source S. Now I'm going to say something about level graph. Let me now level graph. The second one just behind level, below network graph is called level graph. So one is very close to the source O, so the level graph will be increasing on L plus 1. So we have 0, L 0 plus 1 is equal to 1, 1 plus 1 is equal to 2, 2 plus 1 is equal to 3. So basically it will go on increasing 1. Blocking flow includes finding the new path from the portal node capacity. Augmenting path is the simplest path from the source to the sink, which does not include cycles. Just like in Prim's algorithm, we cannot complete cycles. So cycles cannot be complete. Residual and augmenting path can be of two types: non-full forward edges, and we can make augmenting path from non-empty backward edges. A residual graph indicates how much more flow is allowed in the graph network. So before moving to the problem definition, I'll be saying something about the steps that are required for dinic to perform dinic algorithm. First of all, we have to construct a level graph by doing a breadth first search from the source to the level. Then after constructing a level graph, then if the sink was never reached while building the level graph, then stop and return the max flow. And the last one is we have to use valid edges. We have to use the valid edges and do multiple depth first shots from source to sink until a blocking flow is reached, and the sum over the bottleneck value of all the augmenting founds to calculate the maximum flow. So basically what it meant to say is the maximum flow is equal to the sum over the bottleneck value of all augmenting path. So let's go through problem definition. We are going to find a maximum flow for algorithm for a graph. So we have taken a graph and it has a vertex S, P, R, Q, A and T, and we have edges with the values S P is equal to 11, P R is equal to 8, R T is equal to 10, S Q is equal to 9, P Q is equal to 2, Q R is equal to 6, Q A is equal to 9, and A T is equal to 11. So step 1, we have to make network flow. So we have to start with 0. So the 0 means flow. So the 0 in the edge SP means 0 is the flow, and 8 is the cap, and 11 is the capacity. The maximum capacity, the maximum amount of energy that can be transferred through the point S to P is 11, and currently it has a flow of 0. So behind network graph we have level graph and residual graph. Let us take through augmenting path SPRT. SPRT. Now network graph will be look like SPRT. S as the S as the total capacity of 11, P as the SP as the total capacity of 11, PR has the total capacity of 8, RT has the total capacity of 10. So the bottleneck capacity will be 8, as 8 is the smallest among all of them. So the network graph will look like 8 upon SP is equal to 8 upon 11. 8 means the flow, and uh, the number upon the denominator is known as the maximum capacity. Now we have taken the path SPRT. Now let us take a path called SQRT and SQRT. Now SQRT, the total capacity of the edges SQ is 9, PQ is 2, QR is 6, and RT is we have already completed 8 from the above path, so it has the residual capacity of 2. So it has the residual capacity of 2. Let me take you through the path SQ, or let us take through a path SQRT, SPRT. Let me take you through a path SQRT. SQRT. The edges S and SQ has the capacity of 9, PQ has the capacity of 2, and QR has the capacity of 6, and RT has the capacity of only 2. As 8 is the flow and 10 is the capacity, the residual capacity of RT is only 2. So the maximum amount of energy that can be transferred through the vortex R to T is 2. 10 minus 8 is equal to 2. So the bottleneck capacity will be 2, as the minimum value of vortex is 2. So now now the network flow will look like this. SQ is equal to 2 upon 9, P is equal to 0 upon 2, and QR is equal to 2 upon 6, and RT is equal to 8 plus 2, 10 by 10. Now let me take you through another path SQAT. The in previous graph we have SQ is equal to the residual capacity of SQ will be 7, as अब 2 त यहाँ गइसक्यो नि त, 2 भनेको फ्लो हुन्छ, अनि 2 भनेको फ्लो भनेपछि त S देखि Q सम्म गइसक्यो. सो अब यहाँ भनेको 9 minus 2 भनेको 7 हुन्छ S र Q मा हैन, अनि we will remain to S. The S Q is equal to 7, QA is equal to 9, and AT is equal to 11. So the residual capacity will be 7. So the total amount of energy that can be transferred through S to Q will be 2 plus 7 is equal to 9, and QA is equal to 7 plus 9, and A to T will be 7 upon 11. So the level graph will look like this: 0, 1, 1, 2, 2, 3. 0 and 1 are not connected, as the maximum amount of energy that can be transferred is full, 9 upon 9. So we can't send anything. We cannot send anything. So this S to Q will not be connected in level graph, and P to R and R to T will not also be connected in level graph. Like this. Now so we can travel through S to Q, we can travel through P to Q, we can travel capacity 7. We can't travel through P to R. We can't travel through R to R, but we can travel through it as the capacity of residual capacity of 3. PQ has the residual capacity of 2. RQA has the residual capacity of 2, and A to T has the residual capacity of 2. So the so 2 is the minimum. So the bottleneck capacity will be 2, and 8 plus 2 is equal to 10. P to Q, so 2 by 2. Q to A, 7 plus 2 is equal to 9. 9 by 9, and A to T is equal to 9 by 11. अनि हाम्रो रेसिडुअल क्यापेसिटी भनेको चाहिँ क्यापेसिटी माइनस फ्लो हुन्छ. सो the path from S to Q is blocked, and the path from P to Q and Q to R is also blocked. So we cannot go just like anything. So no more paths are there to travel. So the residual graph of this will be look like this. We can also do backtracking. So the amount of the amount of flow that can be still transferred from vortex S to P is 1, and the maximum flow that can be transferred through the vortex P to S by backtracking is 10. So like this we can also make a residual graph. So the level graph will look like this. Ani 0 1 1 2 2 2 3. So the maximum flow is equal to total bottleneck capacity, and now we are going to calculate the total bottleneck capacity. First of all, the bottleneck capacity was 8, then 2, then 7, plus then at last 2. So that 8 plus 2 plus 7 plus 2 is equal to 9. The max flow from source to sink T will be 19. The maximum amount of energy or flow that can be transferred through the sink S through all the vertices to sink T will be 19. So what are as you know, everything has pros and cons, so it has also some limitation. We have to deal about multiple dead ends during the DFS phase. So multiple dead ends means using same route again and again. So while using same routes again and again, it can extend the length of a journey from source to the sink. So these are the limitations of this algorithm. So to conclude, dinic's algorithm is the fastest and most reliable and efficient algorithm to solve max flow problems. The basic principle of this algorithm is maximum flow is equal to minimum cut. So minimum cut. So what does minimum cut means? So the minimum cut means bottleneck capacity. The bottleneck capacity means the smallest amount of value along the vertices that are traveled. So in this algorithm, new ideas like level graph and blocking flow were introduced. So it is one of the fastest and efficient algorithm. So the main idea behind dinic's algorithm is to guide augmenting path from source to sink using a level graph, and in doing so greatly reducing the runtime.